Yeah, control hazards occurs because of the branches. Because of the branches. So if you recall let me share my screen. Okay. So if I share the screen, if you look at here, for branch instructions, the program counter will be updated at the end of execution stage, because in the execution stage, one ALU computes the control and second ALU computes the target address. Second ALU computes the target address. So based on the first ALU output, whether the same branch will be taken or the next branch will be executed, that will be decided. That will be decided, right? So in this, so if you recall the lab which we performed, okay, so in this we use the labels here, right? So in the branch instruction, first it compares the condition. So that is the branch condition. Then it computes the target address, where it should go. So if the comparison is not equal, if R2, R01 value is not equal to 2, then jump to L1, level 1, jump to the target location. Jump to the target location. So this operation is happening at which stage? At the third stage. At the third stage. So that is, if you recall this, the ALU1 is computing the comparison operation and the add sum that computes the branch target address. So mean to say that if any instruction that is following in the pipeline to execute the pipeline, okay, so program counter updates the address of the next instruction at the end of execution stage and during the memory access stage. So by just keeping this point a important takeaway from this control hazard, okay, in this, if you look at that, suppose there is a branch instruction followed by the non-branch instructions. There is a branch instruction followed by a non-branch instructions like move instruction or add instruction or like store instruction, like store byte, any instructions. Okay? That is followed by a branch instruction, suppose. Then in the pipeline, how the hazard comes. In the first cycle, first instruction allowed inside the pipe. In the second cycle, two instructions will be allowed inside the pipe. So first instruction, that is branch instruction, moves into instruction decode stage. And second instruction should be allowed inside the pipe. But don't know whether the same branch will be taken or the not taken is unknown here. So program counter is not yet updated whether this branch will be taken or not taken. That will be only updated during the fourth stage. So these instructions, the branch target instructions, or any fall through instruction, they stop executing. They stop executing. So instruction, the branch instruction 1 goes through instruction decode stage. Here, the branch instruction compare means its condition will be computed and its target address will be computed. And that enters into memory access stage. So program counter not yet updated till now. So the fall through instructions still stops their execution there. Okay. But at the fifth stage, at the end of this fourth stage, if program counter updated that, the branch will not be taken and program counter updated with the address of this instruction, then that will allow inside the pipe. And then the branch target means the next sequential instruction continue their execution. So because of this branch instruction, these instructions are not allowed inside the pipe, that is up to 3 stages. So that leads to execute these 2 instructions in 9 cycles. In 9 cycles. Okay, so then what is the solution for this? The first solution is whatever the ALU is computing, the target address and the condition, if those 2 ALUs, if they moved 1 stage forward, because of the Moore's law, if you have more transistors, you can build more functional units, more ALUs. If those ALUs are moved forward to the stage 2, suppose, so then in the second cycle, instruction 1 enters into the pipeline in the instruction decode stage. Instruction 2 will be bubbled. If here the extra ALUs are added, extra 2 ALUs are suppose added, one to compute the comparison operation, second one is to compute the target, or simply write jump equals to something like that. Okay, so if these are known at this stage, at the end of second stage, then at the third stage, instruction, the branch target instructions will be allowed inside the pipe, because at this end of this second stage only knows that this branch will not be taken, suppose. Okay, and then continue the execution. So this is one solution. It completes its execution in 7 cycles. But whereas if it is unknown, if no fast branch resolution, then they complete in 9 cycles. So this is one of the solution. This is one of the solution, because it leads to a hardware complexity again, adding the extra adders. The another solution is assume that the branch will not be taken. Is another solution. Assume the branch will not be taken. So in that case, the branch instruction will be allowed inside the pipe, and it goes through the upper stages, and the fall through instructions will also allowed inside the pipe, which are non-branch instructions, suppose, and they complete their execution in total 6 cycles. So if this assumption is correct, the branch will not be taken, and forcefully adding the fall through instructions into the pipe, then if this assumption is correct, these 2 instructions completes their execution in 6 cycles. But if this assumption is wrong, assume that branch will not be taken. If this assumption is wrong, then what happens? All the instructions which are allowed inside the pipe after the branch, they must be flushed through. So they treated as wrong instruction, wrongly inserted instructions in the pipeline. So then what to do? Because at the end of this 4th stage only, the program counter updated the address of the instruction 1 only, suppose. The instruction 1. So instruction 2, instruction 3, instruction 4, they allowed inside the pipe. They are at different stages. Execution stage, decode stage, and the instruction fetching stage. So they must be flushed out. So in the write back stage, the first instruction, branch instruction, again it takes. So instruction 2 wrongly inserted, so that must be flushed out. So the memory access stage is not allowed, so that must be flushed. Then instruction 3 also enters into the flush stage, flushing it. It won't enter into execution stage. Instruction 4 not allowed inside the, it get into the the instruction decode stage. It is into instruction fetching stage, but still it entered into instruction decode stage. But after that, its execution won't work because the same branch instruction is executed. So instruction 2 is at instruction execution stage, so it must go through the remaining two stages, memory access stage and write back stage. Then instruction 3 is in the instruction decode stage, so it go through instruction execution stage, memory access stage. Then instruction 3 goes through the execution state, that is flushing. Okay, so instruction 2 flushed in 2 cycles, instruction 3 flushed in 3 cycles, instruction 4 also flushed in 3 cycles. So when instruction 4 moved into instruction decode stage, instruction 1, the same instruction 1 allowed inside the pipe. Then instruction 4 going through this flushing stage, but the same branch instruction executed again. So this is, if the assumption is correct, these instructions will smoothly execute in the pipeline. If assumption is not correct, the key takeaway here is the instructions must be flushed out. Okay. So this is one solution. Another one is branch slot and delay. In slot and delay, if this is a branch instruction and these instructions are non-branch instructions, suppose, then separate these branch instructions and the non-branch instructions. Separate the instructions, okay? Like branch instructions, they keep in delay slot. So if you assume this is one slot, okay, this is delay slot. Delay the branches, and these non-branch instructions, okay, they have given chance first, that not delay slot. So they will be executed first, then the branch instructions. So this is again out of order instructions. So this is called branch. This is called the branch delay and delay slots. Okay. So then the final solution is, this is the branch delay slot which we just observed. The final solution is branch prediction. So this branch prediction is actually a guessing part, adding the additional or parallel hardware to predict whether that branch will be, the currently executing branch will be taken or not taken. So we will discuss this in detail, the branch prediction, in the next class. Okay.